Hi, everybody. So this is our second video. We're going to talk about measurements today. Yesterday we talked about sig figs, how sig figs are really important because we're dealing with physical objects that have physical limitations. And another thing that has physical limitations is our units and our measurements. So for example, measurements depending on material limits, what is a kilogram? So the specific definition of a kilogram is that it is in the picture. You can see that there is this platinum iridium alloy cylinder with a diameter and height of 39 millimeters. This was established in 1889, and for the longest time, that was still used up until I think it was in the 2000s. We actually changed that, but that is the definition of the kilogram. Now, what is the weakness of this measurement? Tiny changes due to absorption. For example, tiny atmospheric particles can actually cling to a solid surface, and that can be measured when you're looking at such a very, very exact measurement. Then there's also the cleaning that they have to do on the kilogram to make sure that it doesn't absorb too much material, and as you transfer it, the scratching from the cleaning as well. So here, this image actually shows the drift over time of these cylinder copies. So they all started, you can see there is a change in mass in micrograms. That is shown right over there. Okay, so the percent change, there is a change in mass in micrograms, and you can see that all of these different models, there are different numbers over here. These numbers are the different models that were given around the world so that people could monitor the kilogram and they could have their own copy of the kilogram. And over time, all of those started migrating. Not many actually stuck around near that zero mark. So right here, that is your zero mark. Anything that's really close to that mark was pretty consistent over time. And you can see that started around 1889, and they started measuring the change in mass around 1900. You can see that about right there. Starts about 1900, okay? So since 1900, over the next 90-ish years, some of these cylinders were actually gaining mass, which is an issue because that means that whatever we're judging a kilogram on is actually changing constantly. So we wanted to avoid that. And several of our other measurements have errors as well. So let's talk about the meter. A meter is different as well. So what are the best and worst ways to measure a meter? So for example, we've got A, B, C, and D. A, the tip of your finger to your nose. So stick your arm out, straight out, the tip of your finger all the way to your nose. That was one way to estimate a meter. The distance light travels in 1/299,792,458 of a second. Then there's the length of a platinum iridium bar stored in a vault. They really liked platinum iridium. Or what is that? 1, 2, 3, 4, 5, 6, 7. Okay, so that's 1/10,000,000th of the distance from the North Pole to the equator. Which of those would be the best way to measure a meter? So the meter actually progressed throughout history. It started as what they called an English yard. Then what they did is they divided the length of Earth along the meridian, which was the distance from the North Pole to the equator. They just divided that length from pole to equator by 10 million and called that good. Then they made their own platinum iridium bar and made it a meter and put it in a vault. And of course, that probably also had some deviation to it as well. And then we eventually got to the distance light travels in some fraction of a second. Now, which of those do we think would be best? Well, tip of your finger to your nose, not great. I don't know about you guys, but Kevin Durant's meter is probably longer than my meter, so that's not a very good estimate. We already talked about the flaws of having some platinum iridium object being just stored in a vault and then slowly changing over time due to atmospheric changes. Even though it's in the micrograms, we don't want to be off. So this would probably be in the micrometers that this is starting to deviate, which is, again, something we don't want. We don't want a meter to be different here than other places. And next we had 1/10,000,000th of the distance from the North Pole to the equator. I don't know about you guys, but I don't want to measure the North Pole to the equator anytime I need to estimate a meter. So the best option we have so far is the distance light travels in a fraction of a second. Now, the reason that we like this definition is that it has nothing to do with planet Earth or any properties of planet Earth. It has nothing to do with a human's arm. It has nothing to do with some bar that we made, and we're humans, we're going to make error. So all of those bars are probably going to deviate ever so slightly. And it doesn't have to do with the changing planet that we live on. So this is just however far light travels if we give it this much time to go, because the speed of light is constant and a second is constant. But we'll get to that. What is the definition of a second? That's going to be important. The goal is just to not have an Earth-dependent definition, which is difficult sometimes. All right, so number 2, which of these have been used in measurement history, and which is the modern way to measure a meter? So spoiler alert, we went over this. I should have looked ahead a little bit better. So modern way to measure a meter is let light travel for a very small fraction of a second. That's your meter. This is actually a modern meter measurer. This sucker can actually measure a meter. So any concerns about the modern meter measure, put that in the discussion board and we can discuss that. Go. So the meter now depends on the second, but how is the second defined? So the second has a very, very specific definition. It is if you measure and study a cesium-133 atom, it is the time it takes for an electron to make a transition from the one stage to the other, 9,192,631,770 times. So that electron, because cesium-133 is not I don't think that's the most stable atom of cesium. So the electron will constantly sit there and make these electron transitions over and over again at the same interval. And as it does so, if you count that over 9 billion times, that would be 1 second. And this is kind of how the atomic clocks work as well. Atomic clocks will use an atom to count a second to make sure that the world clocks are not off. That's why, I don't know if you guys have smartwatches or something that connects to your phone. If my smartwatch doesn't connect every few hours, actually it's more like every few days, but it'll actually be off. I can tell that there's actually, oh, well, that changed to the next minute before my phone does. So if I sync them up, then all of a sudden it gets back into the rhythm, because your smartphones are connected to the internet, your laptops are connected to the internet. They should all run on the same time. This second measurement, we have calculated the error. So there is error in this measurement. And that error is that it is accurate to less than 1 second deviation over 20 million years. So over 20 million years, there will be deviation to that, but it will be less than 1 second. So if we live for, if civilization lasts 20 million years, there might be some deviation to our second measurement. But considering that's not the case, we can negate that error for our purposes. Now, how many sig figs are in this measurement? So if we look at how precise we are trying to be in here. Now, there's no decimal point, remember? So there's the decimal is absent. So we start from the Atlantic, so we'll start from the right. So we ignore that 0 and we count 7, 7, 1. Oh, I'll get my fingers on the screen. 7, 7, 1, 3, 6, 2, 9, 1, 9. So that is 9 sig figs. That is a very precise measurement. And to make such a precise measurement, you need a very precise machine, which is why we have this fancy modern meter measurer here. Went off the screen there. Modern meter measurer. That is a very, very, very precise measuring tool that can measure a very small fraction of a second, which was 1 over, let's go back, this number right here. It can measure that small of a fraction of a second, and it can watch light travel in that time. So do you believe humans can make a device precise enough to make that measurement? That's on you guys to research and study, because it's possible that our counters, our atomic clocks, they may not be as precise as everyone wants them to think. And this modern meter measure may be not as precise as people want to think. So our second may be off. And if our second is off, that means our meter is off, which would basically crumble all of our definitions for units. But again, we're trying to get something that's not Earth dependent. Now, the second definition is kind of Earth dependent because that cesium atom needs to be a certain temperature under a certain amount of air pressure at a certain under a certain force of gravity, yada yada yada. So that is still kind of Earth dependent. I would be curious to know if the second would be the same in orbit, but velocity can also alter your perception of time. As you approach the speed of light, your perception of time changes, and gravity can change your perception of time. If you are in a stronger gravitational field, then you will experience a slower perception of time, which is what happens in Interstellar. They are very close to a black hole. They are within a very strong gravitational field. So I can't remember how long it takes, but like every second is a year. No, a month. I think every second was a month. I can't remember what it was. Look it up. But in that movie, they have a time dilation because they were in a very strong gravitational field, which is real. Interstellar got that right. They got a lot of things right. All right, so our place in the universe. Here we have an approximate masses of various objects. So first, what is the deal with the squiggle in table 1.2? Well, those cannot be approximately accurate. Sorry, those cannot be approximated accurately. So some of those are just vague. For example, shark. That's kind of hard to just say, oh, a shark is this size. There are a lot of different kinds of sharks. Just like there are a bunch of different kinds of humans and frogs. Now, the observable universe, that's a little bit harder to approximate just because that's a lot of things to take into account. But the observable universe, we say, would be approximately 10 to the 52nd kilograms, which means you would have 1 and 52 zeros, and that would in kilograms. Now, the Milky Way galaxy is 10 to the 42nd kilograms. So it sounds like, okay, so it sounds like the Milky Way might be a pretty good fraction of the observable universe. So let's compare some of these. First, let's compare the sun's mass to Earth's mass. The sun's mass is 1.99 times 10 to the 30th kilograms. Okay, so let's get the calculator out. 1.99 times 10 to the 30th. Y'all, I think my calculator died. Okay. Well, that's going to put a damper on all of this. I don't think I have a smart calculator lying around. So that really sucks. I'm going to pause this recording